You know what? Most innovations in financial modeling solve the wrong problem. They aim to make it easier to play around with assumptions, for example. They solve technical problems instead of overcoming the flaws in methodology. Because what's the point in being able to easily change arbitrary inputs? Getting arbitrary outputs faster? I'm Thorsten Rohner, and I'm the founder of Seconomic, a boutique consultancy specializing in building decision support and risk analysis models. The strange thing is that I don't use Excel, but develop my models with Analytica, a modeling platform that integrates visual model building, working with multidimensional data, and guess what? A powerful Monte Carlo simulation engine. To promote the use of Analytica for financial modeling, I run a website called Beyond Excel Modeling. Based on Analytica, I recently developed a financial modeling framework, the Seconomic system, that makes it much easier for me as a modeler to concentrate on the business logic and the risk analysis part instead of tinkering with the financial statements and balance the balance sheet. So what's the point of financial modeling when ignoring risks? Then what's the point of financial modeling in the first place? Making financial projections? Structuring financial deals? Or is it about making better decisions? Or as David Bandel-Hertz, one of the pioneers of Monte Carlo simulation in finance, used to frame it, what makes capital investment decisions so demanding is not the problem of projecting return on investment under any given set of assumptions. The difficulty is in the assumptions and in their impact. Each assumption involves its own degree, often a high degree of uncertainty. I like to think of financial modeling like this: the so-called business analysis lifecycle developed by Professor Tom Grossman of the University of San Francisco. I like it because it puts the discipline of financial modeling in context and is a good picture to remember and explain. So the idea is that you have a certain business situation in the real world, being it a big problem to solve or an important decision to make. To help management gain insights into the situation and help them make better decisions, you build a model. The model is like a sandbox where you can safely play around and experiment without doing much harm until you know what you should do with the real thing. In your model world, you ideally start sketching out a conceptual model as an attempt to understand what the problem is, what decisions to make, what information you need, and how this all fits together and relates to each other. Then you typically fire up Excel and start building the real calculation model. As I said before, this is where financial modelers typically spend the bulk of their time. Only little on conceptualizing and other esoterical stuff, but really heavily on doing spreadsheet wizardry. Once you're done with the model, you can start analyzing model behavior. You're doing sensitivity analyses, scenario planning, or other what-if stuff to test how model outputs change if assumptions differ. I mean, don't get me wrong, playing around with inputs to see how the model behaves is a great way to better understand the model and to test if the model delivers plausible results even for edge cases. I do this all the time while developing a model. But let's be honest, this is the farthest one does typically go. Probabilistic modeling, Monte Carlo simulation, yuck. No one in management would understand if we'd come up with a range of possible results, right? Okay, this might not be always the case, but more often than not, risk and uncertainties are still widely ignored. And you know what? Many people still believe that risk analysis and Monte Carlo simulation is too complicated. It's too time-consuming, hard to do, too whatever, and that best guess models are good enough. Okay, let's jump right into our sandbox here and start playing around with a simple business model. This model is an example of a project-driven business. You see the business logic laid out here. The drivers of the business are those three things. First, you have a number of bids you do each month. You might win some of them, you might lose some. So the success rate is another driver. And finally, there is the size of the projects you win. All three define how much new project volume you generate each month. Down here, we have the capacity of our business. This defines how much of this stream of new projects we can work off, and finally, how much revenue we can generate given the rate we charge per day. You also see that there is a backlog of project volume. This is when our capacity is not able to comprise with new projects. So the remaining volume is piled up here and maybe worked off the next month when there are fewer new projects. The rest of the model is straightforward. The salary per consultant defines the personal cost, and that's it. The rating result per month is simply summed up to give us the yearly operating result. You should keep in mind that this type of model is not restricted to a consulting business. It could be a construction or a production business where you have an uncertain input of new projects, of new orders, or whatever, and a restricted capacity. But let's stick with our consulting business here. What I've shown you here is an influence diagram of the business logic. This is what I meant by the conceptual model before. With this kind of model representation, you can easily understand how the business is supposed to work, even without knowing any number. Isn't that cool? That allows you not only as a modeler to think more clearly about what you want to model, but also to have better communication with other stakeholders about the structure and the design of the model, especially when those other persons are not that deep in the technical details of the model. If you use other tools than Analytica to build financial models, and this is what the majority of folks is doing, you might also have such an influence diagram on a flip chart maybe, or somewhere else. But then you'd need to turn to your Excel spreadsheet or other programming tool to do the real calculation. Well, in Analytica, you just put the calculation logic right into the objects on the diagram. And the formulas are quite easy and simple to understand. Look at this. New projects are defined as the number of bids times success rate times project size. The if statement here simply makes sure that we apply this logic to every month. Or this one, capacity is the number of consultants times productivity per consultant. That easy. And even a more complex dynamic logic to calculate the project backlog over a month is easy to understand. Let's try it out. This is the dynamic function in Analytica. It simply tells the machine how to calculate each value along a dimension. In this case, the dimension month. And it basically has two parts. One to define the first element, and the other to define each element thereafter. So the backlog for the first month is defined as 0, since we want to start from a blank table, plus new project minus our capacity. which is what we can work off from those new projects. If new projects are greater than our capacity, the remainder is the backlog, or otherwise it's zero. And it can't be negative, of course. That's why we have to put this max function around it. Then for each subsequent month, we just need to extend this logic to account for what's the backlog from the previous months. That's pretty simple, right? And the same kind of logic is applied to calculate the actual project days processed. For the first month, it's just either the volume of new projects or the capacity, whichever is smaller. That's why the min function here. And for the following month, add the backlog of the previous month to the new projects. The rest of the calculation is straightforward, just some multiplications or a plus and minus, and a bit of summing up over months to get to the yearly total. Now, with this calculation logic in place, you typically go on and use some best guess numbers for inputs. These little guys here to the left where the model starts. If you have historical or industry data, you might use some kind of average. Say you figured out that you typically make 15 bits per month. So you put this number in. The same thing with success rate. Say you have an overall success rate of 20%. And again, project size is typically, let's say, 50 days. So that's it. Let's check out the results. Oh, and by the way, what you see here is the result for a range of possible numbers of consultants. This is because we defined this variable not just as a single number, but a list of values. And let's assume this is what we want to answer with our model. What is the optimal number of consultants? So in our single value deterministic case, we should come to the conclusion that we need exactly 10 consultants to get the most out of our business. But wait, what if our assumptions turn out to be different? I mean, that's quite possible because, well, they're unknown and hence uncertain, and they're living in the future, so you don't know for sure. Okay, then let's define some variations around them. Let's define a best case or a worst case around our base case assumptions, right? To save us time, and because I knew I would give this workshop, I have already prepared a new version of this model with these cases. By the way, in Analytica, it's quite easy to add new dimensions to an existing model. Just define a new index. This is this little thing here as a list of different items. It could be different cases, different scenarios, etc., but also different products, different regions, currencies, and so on. Any dimension you need in your model. So, having created this case index, we simply need to define the inputs here as a table, indexed by case. And here you have the new case values for all assumptions. And by the way, you don't need to make any changes to the calculation logic. You see, the formulas stay the same even if we now run the model basically 3 times, one for each case. So here are the results. Okay, what does that tell us? When assumptions go down, results also get worse. And when assumptions get better, we don't see any improvement until we reach a capacity threshold, obviously. This is a typical pattern for nonlinear business models. Basically, every time you have capacity restrictions, you'll find this pattern. For our decision problem, it seems like in the best case, we could increase the number of consultants at least to 15, maybe even more, before our capacity might outpace the volume of new projects. And in the worst case, we might want to reduce the number of consultants probably below 8. Is this of any help for the decision maker? Well, not really. It just tells if everything goes extremely well, we should hire like crazy. And if things go extremely south, we should better lay off people. Now, that's what we've known before, right? So that's no surprise, because this kind of analysis, which is found quite often in financial models, inherently presumes that everything bad happens at the same time in the worst case scenario, while everything is perfect in the best case. And we all know that this is extremely rare. So it's probably better to test certain combinations of assumptions, right? Let's try this out. I call this a multi-parametric analysis. Here we have the same model with the same variations for our inputs, but this time these are not tied to specific cases, but treated individually. That's also very easy in Analytica. You can define a variable not just as a single value or a table like before, but also as a simple list of values, as you see here. And again, no changes to the calculation logic required. When we evaluate the result, you see there are a couple of new dimensions. Each input, because we defined it as a list of values, becomes its own index. Now, when we toggle through the various possible combinations, we can get really sick by the number of different possible outcomes. Gosh, I don't know how you feel, but I'm actually more confused than before. The reason for this is that even in this tiny little example here, we have 3 times 3. This is 27 possible combinations. I've separated these combinations here to put them next to each other so you can see what happens. Every line here represents a possible combination of the input values. And each line might have its individual optimum value for the number of consultants. The only thing you can really see from this analysis is the potential solution space, as a mathematician would put it. And that's all you can find out using deterministic sensitivity analysis. We can tell how likely every possible value is, but that's what we really want to know, right? So here comes risk analysis. Basically, what we're doing with quantitative risk analysis and Monte Carlo simulation is putting a likelihood or a probability to each value of an input. That's why we call this probability distribution. Now let's see if we get better results if we use a probability distribution for each input instead of just 3 distinct cases. Here's the same model again. This time you might notice the different shape of the inputs. This comes because in Analytica, when you define a variable as a probability distribution, it automatically depicts this object like this, as an oval. This way you can easily spot uncertain variables in your model diagram. Now, when we look at the definition of bids, you see I used a log normal distribution with a mean value of 15 and a standard deviation of 2. Rounded so we get whole numbers. The distribution looks like this. You see, with these parameters, it could be roughly anything between 11 and say 20. The point here is not the exact shape and size of the distribution. This is purely made up by me for this example. In the real world, there are various techniques to determine these distributions, but often, if you do the risk analysis right, the edges of the distribution go beyond what you typically consider best or worst in your parametric analysis. I also changed the model a bit in that I used a binomial distribution for successful bits. A binomial distribution is typically used when you have a number of individual independent trials. This is the number of bits per month in our case, and a probability of success. This gives us the distribution of successful bits. So for successful bits in our model, everything is possible from 0 to, say, practically 7. Finally, for project size, I also used a log normal distribution. Now, let's check out the result. And did I mention that you don't need to touch the calculation logic in the model? Wow, holy crap. That doesn't look any better than before. Even more possible combinations. But that's what the Monte Carlo engine is actually doing. Drawing random numbers from input distributions and calculating the model 1,000 times, for example. But wait, there is relief. Some combinations are more likely than others, or technically, some values appear more often than others in the simulation. That means we can build a probability distribution for the result in the same way we have it for each input. In Analytica, we can easily choose different types of diagrams to depict these distributions. For instance, if we look at the classical probability density chart, we see this strange distribution. Let's think about why that is. It looks like that we can't get over some threshold, either up or down. Obviously, we can make more profit than we're able with our workforce, even if there is more work to do. So that's the upside boundary. And likewise, we can lose more money than we have to pay for our workforce, even if there is no work to do. That's the downside limit. Nice insight, right? To make the result comparable to our previous analyses, we should choose the probability bands chart, I think. This at least gives us a better sense of not only what's possible, but what's more likely. For instance, negative results are possible, but 50% of outcomes should fall between these two lines, this one and this one, the 25 and the 75 percentile. Oh, and we can also calculate the probability weighted average of all simulated results, the value also known as the expected value or the mean value of the distribution. That's probably one good measure we'd use to determine the right size of our workforce. And here, we'd rather go for 12 to 14 instead of the 10 consultants the deterministic analysis had suggested. So that's how including risk could change our mind. But wait, there's more. You might have noticed the title of the model read Naive Risk Analysis. I call this naive because we just replaced the single value in the assumptions with a distribution without thinking any deeper about the model itself. Let me show you what the problem is, and it has something to do with this quote. A theory should be as simple as possible, but no simpler. And I think in this case, it is. So here I added this compare node so we can see the simulated values next to each other. When we click through the simulation scenarios, we quickly realize a profound flaw in our model. Obviously, in each simulation, we use the same random number for each month. That means we inherently assume when we have a low number for bits, this number will apply to all months of the year. But that's not what we wanted, right? We know that there's uncertainty around the number of bits per month, but of course, for each month individually. That means we want to have individual, independent random numbers per month. And the same is true for success and project size, of course. If we don't refine our model and stick with our first naive approach, we're going to vastly overestimate the uncertainty in our business model. Because if things go down, they go down for every month and vice versa. But that's not true, because in reality there are bad months offset by good ones, right? So here I prepared a better, more refined model. Looks the same on the surface, but I used an additional parameter in the distribution function. Here, over month. Over month forces the simulation to draw separate random numbers for each month. Let's look at the simulations again. And we see that we now have different numbers in each month. Now, let's check the results. It seems the probability band looks much smoother than before. This obviously comes from all the smoothing, offsetting effects we now have in our model. And there's another interesting observation. When we look at the probability density again, we don't see the two sharp boundaries anymore. There's only one boundary to the right where we hit the capacity limit of our workforce. But the downside is way less dramatic as it seemed with our first naive model. And when we toggle to the higher numbers of consultants, we realize that it's ever less likely to hit this capacity constraint. This is what we could have seen in the probability bands chart, where the upper probabilities kind of collapse into 1 when we hit this threshold. Does our refined model change our decision? Well, not dramatically, but it seems that the optimum shifted slightly to the left again when we look at the mean value. But the mean value or expected value is now quite a bit higher than before, around 1.6 million instead of 1.2 million. So a more in-depth risk analysis must not result in worse outcomes. Isn't that great? Maybe we can do even better. What do you think? Let's have a look at the simulation numbers again. Do you spot the problem? Exactly. The project size. We simulate one project size and then apply this number to all projects that we won this month. But that's not what we actually wanted. We know that each project has a different size. So let's implement this in a new version of the model. What I did here is introducing a new index for project, defined as a list going from 1 to 11, roughly what's possible given our assumptions. Now we can assign an individual value to each new project per month. We simply need to add this additional index to the distribution function here. When we now look at the numbers, we see how a different project size is used for each simulated new project. And that's exactly how reality works for our business model. Look at these nice patterns for new projects over a month. Doesn't that look interesting? Or the possible developments in the backlog. Fewer consultants result in greater backlog. By the way, adding this project as a dimension we just need temporarily in our model is an example of the rare cases where we need to adjust the formulas in Analytica a bit. For the backlog as well as for processed days, we need to sum over projects since we don't need this additional dimension in our results. Speaking of results, they are not fundamentally different, yet slightly improved in the way they measure and represent the uncertainty around the business that we want to model. As expected, the range of downside potential is even more narrowed, and the expected value is further increased a bit, from a little shy of 1.6 million to almost 1.7 million. Now, what's the takeaway of all this? We've seen that without taking risks and uncertainties into account, we just create, arbitrary results. And that's not getting better if we use average values for model assumptions. As Sam Savage puts it so aptly, plans based on average assumptions are wrong on average. This is always the case when you have capacity constraints or something that limits the upside but exposes you to the downside. Look at this. When we compare the deterministic model with the full risk analysis, you see the difference. The average value we can expect is much lower than the previous optimum. And the new optimum is also somewhere else. But most importantly, when we look at the probabilities, we realize that the probability to reach the deterministic result is practically zero. That's what a financial model should be there for. Making a business logic transparent so we can eventually apply advanced risk analysis to make better decisions. In my experience, almost no business model is purely linear. So ignoring risks or playing around with arbitrary assumptions is a bad idea, and sometimes outright dangerous. In the end, it's not necessary to ignore risks and uncertainties anymore. Come on, it's 2020. We don't need to constrain ourselves to still pictures where we can have the full scene, the full movie. This is what we basically do when we do risk analysis and Monte Carlo simulation. We replace a single image or a series of single images with a complete movie. And it's easy nowadays with the right tools. And that's why I use Analytica for financial modeling and risk analysis. When I first came across Analytica, I wasn't actually searching for a new modeling tool to replace Excel. I just had the need to visualize the complex logic of a pretty large planning model in Excel I had built for a large retail and mail order company and explain it to various stakeholders. Most of them were not practically Excel wizards. So I started drawing diagrams with boxes and arrows in Microsoft Visio, trying to make the calculation flow visible and easier to explain. It was still a mess, especially because I had to adjust the picture manually every time I made changes to the Excel model. And I needed to change the model often. Then I found Analytica, and it not only allowed me to see the model structure as influence diagrams, but I also could use the diagram to navigate large models more easily, put in the most complex multidimensional calculations right into the objects in the diagram, and could even run Monte Carlo simulations where I could see the results for every variable in the model, not only for those I dedicated as an output. I'm not saying that you need Analytica to build probabilistic models. You can stick with Excel and third-party add-ins or use data tables to do the trick. But personally, I find Analytica so much easier to use. So the only wish I have, don't ignore risks anymore when you build financial models. Please.